This video covers Part 1 of Section 1.1, Statements and Logical Connectives. The study of an area of mathematics begins by first defining the mathematical objects to be studied. For instance, in plane geometry, the objects in question include points, lines, circles, triangles, and parallel lines. In linear algebra, the objects include vector spaces, subspaces, linear transformations, and eigenvalues. In abstract algebra, the objects include groups, rings, fields, homomorphisms, and algebras. After making these definitions, the mathematician then proceeds to make statements about the mathematical objects. There are two basic types of mathematical statements, axioms and theorems. Axioms are statements that are assumed to be true. In the past, axioms were statements considered to be so obvious that their truth was self-evident. For instance, the ancient Greek mathematicians considered the following statement to be an axiom of geometry. For any two distinct points, there is exactly one line that passes through them. This type of thinking assumes that the mathematical objects, in this case points and lines, exist in the physical world. In modern mathematics, the mathematical objects in question are often abstract entities which need not have any connection to the physical world. The axioms in this modern viewpoint are then just assumptions that are part of the definitions of the mathematical structures under examination. For instance, in abstract algebra, a group is defined to be a non-empty set of objects together with a binary operation or rule for combining pairs of objects from the set, which satisfies four properties: closure, associativity, the existence of an identity element, and the existence of inverses. The set may consist of objects from the physical world or may be purely abstract. The four properties in the definition are called the axioms of the group. Even though the objects in question may be purely abstract, mathematicians still refer to the axioms as being true. The other type of mathematical statement is a theorem. Lemmas and corollaries are special types of theorems, but theorems nonetheless. In the past, mathematicians considered theorems to also be true statements. However, the truth of a theorem was not self-evident, as was the truth of an axiom. Instead, its truth had to be deduced from the axioms using the laws of logic. A proof of a theorem was a valid logical argument verifying the truth of a theorem. For instance, the statement from geometry, the sum of the angles of any triangle equals 180 degrees, was considered a theorem rather than an axiom, since its truth is not self-evident. In the modern point of view, a theorem is still a statement which is a logical consequence of the axioms. A proof is then a valid logical argument demonstrating that the theorem does indeed follow from the axioms, as opposed to demonstrating the truth of the theorem. Even though it may not be accurate to refer to the truth of a theorem or of an axiom, mathematicians today nevertheless use this terminology as a shorthand for stating that the theorem is a logical consequence of the axioms. So, to begin the study of mathematical proofs, we need to first understand how to determine the truth or falsity of a statement. For many statements, their truth value follows immediately from the definition of the mathematical objects. For instance, it follows immediately from definitions in trigonometry that the statements cosine of 2 pi equals 1 and the function f of x equal cosine of x is periodic with period 2 pi are both true. It follows immediately from definitions in algebra that the statement 2 plus 3 quantity squared equals 2 squared plus 3 squared is false. For more complex statements, such as if cosine of 2 pi equals 1, then the function f of x equal cosine of x is periodic with period 2 pi, it may not be immediately clear whether it is true or false. It turns out that the truth value of such a compound statement depends upon the truth values of its component simple statements and on characteristics of the connective involved in the compound statement. We'll start by examining this relationship. In your English courses, you learn there are four types of sentences: declarative, interrogative, exclamatory, and imperative. A declarative sentence states a fact or expresses an opinion and ends in a period. An interrogative sentence asks a question and ends in a question mark. An exclamatory sentence expresses emotion or feelings and ends in an exclamation mark. Finally, an imperative sentence gives a command and may end in a period or exclamation mark. We're going to be concerned almost exclusively with declarative sentences. which form the basis of our fundamental definition for the study of proofs. So we're going to define a statement or proposition to be a declarative sentence that is either true or false, but not both. The truth or falsity of a statement is referred to as its truth value. So a statement is a declarative sentence with a definite truth value. Statements are typically denoted by lowercase letters such as P, Q, R, S, etc. For our first example, we want to determine whether or not each of the following is a statement. So we'll start with Abraham Lincoln was the 16th President of the United States. This is a declarative sentence and has a definite truth value, namely true. Therefore, this is a statement. Next we have 2 plus 5 equals 6. While this may not look like a sentence from an English course, we can write it out in the form 2 plus 5 equals 6 in words. In this form, we see that this can indeed be viewed as a declarative sentence. Since it has a definite truth value, namely false, then this is a statement. Next, we have 2 plus 5. As in the previous example, we can rewrite this using words as 2 plus 5. This, however, is not a declarative sentence, since it does not contain a verb, so is not a statement. We can also see that a fragment like this does not have a definite truth value. Try referring to 2 plus 5 as being either true or as false. Next we have, is e to the pi greater than pi to the e? This is an interrogative sentence, not a declarative sentence, so cannot be a statement. We also see that an interrogative sentence like this does not have a definite truth value. While it may be appropriate to respond true or false to a question like this one, it does not make any sense to say the question itself is either true or false. Next we have 2 plus 5i is greater than 1 plus 4i. In this sentence, I refers to the square root of -1, so both 2 plus 5i and 1 plus 4i are complex numbers. This is a declarative sentence. However, as you may learn in one of your advanced mathematics courses, there is no way to define a relation of greater than for the set of complex numbers that satisfies the properties we expect of such a relation. So this sentence does not have a definite truth value and therefore is not a statement. A similar sentence would be something like, an artichoke is greater than a cucumber. Again, there is no greater than relation that can be defined for vegetables, so the sentence does not have a definite truth value. For our next part, we've got the 10 to the 50th digit in the decimal expansion of pi is 5. This is, again, a declarative sentence. At this time, the decimal expansion of pi has been computed to about 10 trillion, or 10 to the 13th places. It will likely be a very, very long time before the 10 to the 50th digit is computed. While we do not currently know what the 10 to the 50th digit is, we do know that it is either 5 or some other digit, so the sentence has a definite truth value. This is therefore a statement. For h, we have 2x plus 1 equals 6. This equation can be put in the form of a declarative sentence, 2 times x plus 1 equals 6. This is not a statement, however, since it is neither true nor false. Its truth value depends upon the value of the variable x. For instance, when x is equal to 5/2, the sentence will be true, but when x is any other number, say x equals 3, the sentence will be false. A sentence of this type, which contains one or more variables, is called a propositional function or a predicate. A propositional function becomes a statement when we substitute specific values for its variables. And so we'll be examining propositional functions in Chapter 2. Next we have x plus 2 quantity squared equals x squared plus 4x plus 4. This equation can also be written in the form of a declarative sentence and is similar to the preceding example in that it contains a variable, x. However, this sentence is true for all real number values of the variable x, so it does seem to have a definite truth value. But what if we substitute something other than a real number for the variable x? For instance, what if we try to substitute something like a set for x? The resulting sentence will basically be nonsense and will not have a truth value, so will not be a statement. So we do not consider this sentence a statement, and in general, we will consider any sentence containing a variable to be a propositional function, not a statement. For our last example, we have this sentence is false. This is a declarative sentence. However, it does not have a definite truth value. To see this, suppose we assume the sentence is true. Then, according to what the sentence is telling us, we should conclude that the sentence is false. On the other hand, suppose we assume the sentence is false. This leads us to conclude that the sentence is true. Since the sentence cannot be both true and false, it must be neither true nor false, and so is not a statement. A sentence of this type, which appears to be both true and false, is referred to as a paradox. Now we saw that the sentence 2x plus 1 equals 6 in the above example is a propositional function and not a statement, since its truth value depends upon the value of the variable x. Propositional functions occur in everyday speech as well. Strictly speaking, a sentence such as "today is Monday" should be considered to be a propositional function, with today representing a variable. Often, however, such sentences are treated as statements where the variable today is assumed to equal a specific value. Next, we want to look at compound statements and logical connectives. Statements may be composed of two or more component statements linked together by one or more logical connectives. Such statements are called compound statements. The five most common logical connectives are not, and, or, if-then, and if and only if. A statement which does not include any of the logical connectives is called a simple statement. For our next example, we want to determine the component simple statements of the following compound statement. If 7 is an odd integer and 6 is an even integer, then 42 is an odd integer. Now we recognize that this is a compound statement because it contains two of our logical connectives. This contains and also if-then. And these connectives link together the component simple statements 7 is an odd integer, 6 is an even integer, and 42 is an odd integer. Now the truth value of a compound statement depends only upon the truth values of its component simple statements in a way determined by the logical connectives and not on the component statements themselves. So for any compound statement that has the form if P then Q, where P and Q represent the component simple statements, the truth value depends only on the truth values of P and Q, and not on the statements P and Q themselves. We now want to look at the definitions of our logical connectives. We'll define each of our 5 logical connectives by specifying the truth value of a compound statement which contains the connective. So start by letting P and Q represent statements, and then the negation of P, which is denoted using a tilde symbol in front of P, which is read not P, is true precisely when P is false. Next, the conjunction of P and Q, which is denoted with an upside-down V symbol, sometimes called a wedge, is read P and Q, is true precisely when P and Q are both true. Third, the disjunction of P and Q, which is denoted P with a V symbol Q, which is read P or Q, is true precisely when at least one of P or Q is true. This is referred to as an inclusive OR. Fourth, the conditional P implies Q, which is denoted using a right-pointing arrow, which is also read if P then Q. This is true except when P is true and Q is false. The component statements P and Q are called the hypothesis and conclusion, respectively, of the conditional statement. Finally, the biconditional P if and only if Q, which is denoted with a double-pointed arrow, is true precisely when both P and Q have the same truth values, either true or false. Expressions such as not P, P and Q, and P implies Q, where P and Q are variables representing unspecified statements, are called statement forms, or statement formulas. We can use the definitions to determine the truth value of compound statements by first determining the statement form corresponding to the statement, as shown in our next example. In this example, we want to translate the given compound statements into symbolic form with statement variables p, q, r, etc., representing the component simple statements. Then determine the truth values of the component simple statements and use these to determine the truth value of the compound statement. For our first statement, we have if 7 is an odd integer and 6 is an even integer, then 42 is an odd integer. The component simple statements of this compound statement are 7 is an odd integer, 6 is an even integer, and 42 is an odd integer. So we define our statement variables as shown. So P represents 7 is an odd integer, Q represents 6 is an even integer, and R represents 42 is an odd integer. Substituting the statement variables into the compound statement, the statement becomes if P and Q, then R. And this has symbolic form, P and Q implies R. Now the component simple statements have truth values, P is true, Q is true, and R is false, where T means true and F means false. Substitute these into the symbolic form to determine the statement's truth value. So we have P and Q implies R is going to be true and true implies false. And according to the definition, true and true is true. So this is equal to true implies false. And now, according to the definition of the conditional, when the hypothesis is true and the conclusion is false, as we have here, true implies false is false. So we conclude that this statement is false. For our next statement, we have 42 is an odd integer if and only if 7 is an odd integer and 6 is not an even integer. This compound statement has the same component simple statements as in part A, so we can use the same statement variables. Replacing the component simple statements with the statement variables, we can write the compound statement as R if and only if P and not Q. This has symbolic form R if and only if the quantity P and not Q. The statement then has truth value false if and only if true and not true. Not true is false, so this becomes false if and only if true and false. And true and false is false, so this simplifies further to false if and only if false. Now, according to the definition of the biconditional, false if and only if false is true. So our statement is true. For our next example, we have the statement if sine of 0 equals 0 and sine of pi equals 0, then the sine function is a periodic function with period pi. The component simple statements of this compound statement are P will represent sine of 0 equals 0, Q will represent sine of pi equals 0, R represents the sine function as a periodic function with period pi. So substituting the statement variables, the statement can be written as if P and Q, then R. And the symbolic form is then P and Q implies R. The component simple statements have truth values, P is true, Q is true, and R is false. So the compound statement has truth value, true and true implies false, and true is true, so this simplifies to true implies false. And now, according to the definition of the conditional, true implies false is false. So this is a false statement. For our fourth example, we have the statement, if the sine function is a periodic function with period pi, or sine of pi is not equal to 0, then sine of 0 equals 0. We can again use the same statement variables as in part C. The compound statement can then be written as if R or not Q, then P. And this has symbolic form. R or not Q implies P. The compound statement then has truth value. False or not true implies true. Not true is false, so this simplifies to false or false implies true. And false or false simplifies to false, so this becomes false implies true. And now, according to the definition of the conditional, false implies true will be true. So our statement is true. A quick comment about notation. As you can see from the previous examples, statement variables can, and often do, involve various mathematical relations and operations, and so may contain mathematical notations such as equals or less than. In particular, because the statement variable may include an equal sign, we do not want to use the equal sign when defining statement variables. This may result in confusing expressions like p equals quantity 3 plus 4 squared equals 3 squared plus 4 squared, or q equals sine of pi equals 0. The appropriate way to avoid such confusion is to use a symbol other than the equal sign when defining our statement variables. For that reason, we use a colon. So for these statement variables, we would write p colon 3 plus 4 quantity squared equals 3 squared plus 4 squared, and q colon sine of pi equals 0. We do, however, use the equal sign when indicating the truth values of statements. So for instance, these statements have truth values, p is false and q is true. And this concludes our first video for section 1.1.